Okay, so welcome back to this set of videos. This is the second video that I'm recording that surrounded the derivation around the J statistic, which allegedly is a chi-square distributed random variable with n minus k degrees of freedom. So what we did in the first video was to show the rank as the asymptotic variance covariance matrix GT. If you haven't looked at that video, do that before you continue. Now this video is concerned with the next result, 2a on slide 89 in the script, and the statement is that you have a vector of standard normally distributed random variables that's collected in a vector x, and you have a symmetric matrix which is also square, so it's a symmetric and square matrix. It's an n by n matrix, and if you use these two objects and compute a quadratic form, x prime ax, a by the way is non-random, the result is a chi-square distributed random variable which has rank, which has degrees of freedom equal to the rank of the matrix A. But this holds true if and only if, that's if EIFF, if and only if A is idempotent, that is, if you can take the matrix, multiply it with itself, and the matrix comes out again. So, in order to understand these results, or this result, you have to think a bit about properties of symmetric matrices, symmetric and square matrices, and idempotent matrices. Those results are a bit unstructured, collected in Green's, William Green's web appendix to his book on econometrics, and we need to assemble sort of these results such that we can make use of them for our purposes. This 2a result is an important intermediate result on our way to understanding why the J statistic is a chi-square distributed random variable. So on this slide, I've restated the thing that we want to show. Obviously, one thing to note is you could, for instance, use for A the identity matrix of order n. Well, that's definitely a symmetric matrix. The identity matrix, it's a square matrix, and the identity matrix is also idempotent, right? You multiply the identity with itself, and you get the identity matrix again. So if you use this matrix for A, right, what you will get is as a quadratic form x prime identity matrix x, and that is the same thing as if you would say, okay, let's take the sum from I to 1 to n, and take the elements of the vector I, square them, and these elements are standard normally distributed random variables, and then obviously you get a chi-square distributed random variable with the degrees of freedom equal to n, right? So x, the vector x would consist of the element x1 till xn, and each element xi would be a standard normally distributed random variable. They're also independent, so the result obtains. The point of the statement here is that it could also use a different matrix than the identity matrix to achieve the same result, in the sense that compute this quadratic form using another matrix A, not the identity, and out comes also something that is chi-square distributed. However, as we shall see, as the degrees of freedom of the chi-square random variable will not be n. You will have less degrees of freedom than n, and the degrees of freedom is actually determined by the rank of A. As a matter of fact, the identity matrix is the only symmetric and square and idempotent matrix which is of full rank. All other idempotent matrices are of reduced rank. Every idempotent matrix is symmetric and square, but only the identity matrix has full rank. All the other idempotent matrices have reduced rank. Why this is so, we shall see as we go along. Okay. So I like to consider the result. I would like to structure these results in two parts, indicated by R1 and R2, which I'm going to refer to a bit later. So this first set of results indexed by R1 is concerned with matrices column sigma, which are symmetric and square, S and S matrices. So the dimension is n by n, so yes, we have a square matrix, and this matrix is also symmetric. Okay. Now, what we can look at then is sort of result number R1A, and that is a result that is concerned with the n eigenvectors of that matrix sigma. So I like to collect these eigenvectors in a matrix. Call this matrix big C. So this is an n by n matrix C, and this matrix contains the eigenvectors in its columns. Okay. So I collect these n eigenvectors in the columns. So all these guys are n by 1 column vectors, and they contain the eigenvectors of the matrix sigma. Now it turns out that these eigenvectors of a symmetric and square matrix, they are orthonormal. That is, if you take the eigenvectors and compute the inner product of them, you'll get either 1 if you take the same eigenvector and take its inner product, or if you take the outer product of different eigenvectors and out comes 0. So what happens is, if we compute C prime C, right, computing these inner products of the eigenvectors, out comes the identity matrix. Okay, so these eigenvectors are orthonormal. And that is an important one to take away. This is for a symmetric and square matrix. It does not hold for square matrices which are not symmetric, but for sigmas being symmetric and square, this is an important result for us. Okay, maybe a little recall is in order here. How do we get these eigenvectors? So it's a result of this operation to say, okay, take the matrix sigma multiplied with C, that's one eigenvalue, is a small c, and these c's solve the equation which has on the right hand side a lambda times c. So in lambda is then what we call an eigenvalue. C is one of the eigenvectors, which shows up left and right. Okay, so that means basically the solution is obtained by setting sigma minus lambda times the identity matrix times C equal to 0. So, and that gives us an idea how to compute the eigenvalues. So we're going to choose the eigenvalues such that this matrix is singular, right? Not a full rank. Okay, and from solving this, I was choosing lambda such that the determinant of that matrix is 0. There actually is not actually one solution, but there are up to n possible solutions. First solution could be lambda 1, and that could be used then to figure out the associated eigenvectors C1 and so forth and so forth. This is the n solution, lambda n, and that would give you the associated eigenvector Cn. So that's what we do to retrieve eigenvectors and eigenvalues of square matrices. And it happens to be the case that these eigenvectors that you get in this way are also orthogonal. Okay. So essentially what we can write here is that for sigma being symmetric and square, S and S, the resulting eigenvectors are orthogonal, and they have unit length. Or we can make them to happen to have unit length. They can be normed such that they have unit length. They are orthonormal vectors. Okay. Now, what also happens is that these eigenvectors are real. They contain only real numbers, and they're also distinct. Okay, n distinct eigenvectors are there, and they are all real. Now, this equation that gives us the eigenvectors can be written in a compact way. In that I say, okay, this is sigma, the matrix as it is. Now I'm using the big C here, which has in its column those n eigenvectors. So this is the n by matrix big C. This is my n by n sigma, and that is equal to C times big lambda, and this big lambda that we have here collects on the main diagonal the eigenvalues. So we have lambda 1 here, lambda 2 here, lambda n here, and off the diagonal I have 0, so it's a diagonal matrix. Okay. So this holds basically for any that can be done for any square matrix. Not necessarily must that matrix be symmetric. That's a possibility to write to express sort of sigma, the matrix, and its eigenvalues and eigenvectors in that form. That's always possible. However, if you have a matrix sigma, which is not only square but also symmetric, then we can see some interesting results which are extremely helpful for our purposes. Now, let us take the equation and multiply, post-multiply both sides of the equation by the transposed matrix C. Now in C prime, the eigenvectors are in the rows, so we have sigma C prime, and that would be C lambda C prime. Okay. So recall from the result that we had earlier that C prime C gives the identity matrix. Okay, and down here we have C prime, so we have the transpose of that object, C prime. Okay, so we have this result that the up here that the eigenvectors are orthogonal, which we can use down here, where we have the expression C prime. But this is actually also the identity matrix, and this is because see, what we have is that C prime C is the identity matrix, right, the orthogonality, and that will imply that C prime obviously can act as the inverse of C, but that implies that C to the minus 1 would be the identity matrix, and that's the same thing as C prime, which is what we have standing on the left-hand side of the above expression. Okay, so this is actually the identity matrix on the left-hand side of the equation. So what we get is the important result that sigma can be represented as a function of its eigenvectors, its eigenvalues collected in this diagonal matrix, and its eigenvectors again. And we call this the spectral decomposition. The spectral decomposition of a symmetric and square matrix sigma, and that is our result R1b, the spectral decomposition, an important result to take away, because it's going to be referenced later on, the spectral decomposition of a symmetric and square matrix. There is an auxiliary result to that R1b result, which is not absolutely necessary for our purposes, but it's worthwhile noting it. So we have the possibility to write C prime sigma C in the following form. So we have C prime, and then we write sigma in its spectral decomposition. And what we get from the orthogonality of the eigenvectors, we get identity times the diagonal matrix lambda times identity, and that would be lambda again. And this is one possibility to make a so-called diagonalization of the matrix by pre and post multiplying it with the matrix sigma with its eigenvectors. So we call this a diagonalization. The diagonalization of a symmetric and square matrix sigma. That would be my what we could refer to as a result R1c. But as I said, we don't need that result strictly for what's going to follow. What we need, however, is from the spectral decomposition the information that we can retrieve the rank of the matrix sigma, of this symmetric and square matrix sigma, by taking a look at the spectral decomposition. So the rank of sigma is then the rank of C lambda C prime, but due to a result that is known as the product rule, you can actually find that in Green's matrix appendix, and the product rule states that if you're interested in the rank of product of three matrices, A, B, and C, which are conformable, and A and C are non-singular, and n by n matrices, so they are square matrices, the rank of that product of the three matrices, two of which, A and C, are non-singular, they are full rank, and in this kind of case, the rank of this product is determined by the rank of the matrix in the middle, that is B. Now, that's the so-called product rule, which is important for our purposes. Now, in our context, the rank of sigma is then determined by the rank of lambda, the matrix in the middle, this diagonal matrix in the middle. Here in our context, we should note that C1, C2, and Cn are orthogonal vectors, and they're all distinct. So it implies that the matrix C, which contains the eigenvector, is a full rank. Okay, and that these matrices are invertible, they are non-singular. So, for this symmetric and square matrix sigma that we have at our hand, the rank is actually determined by the rank of lambda. And lambda, note that again, lambda is a diagonal matrix. And the rank of diagonal matrices is of course easily found out. Just take a look at how many non-zero eigenvalues you actually have on the main diagonal, right? If some of these guys happen to be equal to 0, then you see immediately that the rank of the matrix is going to be reduced. Okay, and if you want to write this down, that's inside. We can give it an index. This is our result R1e. That the rank of a symmetric and square matrix, call it sigma, is equal to the number of non-zero eigenvalues. Of that matrix, right? So again, let's write it here. Lambda is the matrix that collects all these eigenvalues of sigma, and we need to see how many of these eigenvalues are actually non-zero. Okay, so it can be the case that lambda can have many zeros, or can have zeros on the main diagonal. In which case lambda would not be of full rank, but it should be noted that the eigenvalues C1, C2, and Cn, these orthogonal vectors, they are all distinct. No, it is only the eigenvalues that some of them two or so, maybe 0 actually. Okay, so it's the number of non-zero eigenvalues that determines the rank of a symmetric and square matrix sigma. That's a very important result for us to store away. Okay, and that concludes the collection of results indexed R1. I now turn to the results indexed R2, and these R2 results are concerned with symmetrics and square matrices again, but matrices which are also idempotent. Okay, so we call these matrices A, symmetrics and square and idempotent matrices for our purposes, and these matrices have the property of when you multiply them with each other, you get the matrix again. Okay, now result R2A. What we can do as with any symmetric and square matrix, we can apply a spectral decomposition, right? So as we've learned earlier, we can make a spectral decomposition invoking eigenvectors and the eigenvalues. Right? This is something that we know from result R1b, a spectral decomposition applied to a symmetric and square matrix that also happens now to be idempotent. Now, if it's idempotent, we can multiply the matrix with each other, A times A, okay, and see what happens. So you have C lambda C prime, C lambda C prime, okay. What we also know from symmetrics and square matrices, the eigenvectors are orthogonal. So what we had earlier is that C prime C is actually the identity matrix. That's a result that we have from R1, okay, because of the orthogonality of the eigenvectors of a symmetric and square matrix. So we can write AA as C lambda identity lambda C prime, which is the same thing as C lambda lambda C prime. Right? Lambda is a diagonal matrix. The diagonal matrix is symmetric. So lambda is equal to lambda prime. Writing it extensively, what we have is C, and then we insert lambda times lambda. Well, lambda is diagonal, as I said. You multiply it with itself, so what you're going to end up with is a matrix that has on the main diagonal the elements of lambda to the square. So these guys are on the main diagonal, and I collect them off the diagonal. I'll only have zeros. I have C prime. Now, A times A should give us should give us A if the matrix is idempotent, right? But the only chance to ensure that the right-hand side again gives you A is when you take a look at the diagonals of this matrix. So you need to get lambda out of it again, right? C lambda C prime. So the only chance that A times A actually is A is that the eigenvalues have to be either 0 or 1, because then the eigenvalue to the square gives the eigenvalue itself. And there are just two numbers, 0 and 1, which you can multiply or take to the square, and you get the same number out of it. Okay, so write this result down. We have the result that A times A is only C lambda C prime, which is A. It only happens if these eigenvalues, lambda 1 till lambda n, are either 0 or 1. Okay. And that's the important result associated with symmetric square and idempotent matrices. So we can actually conclude that a symmetric and square matrix, which is idempotent, okay, such a matrix A has to have eigenvalues which are either 0 or 1. Right? Otherwise, it would not be an idempotent matrix. Okay, so there's a particular shape of this matrix A, which or in particular the matrix lambda that is associated with A collecting its eigenvalues. One of the results, one of the implications that we have is that the rank of the matrix A is the same as the rank of lambda. Right? That's nothing new. That's what we already have. A is a symmetric and square matrix, and the rank is determined by this lambda matrix. C result R1D up there. But what we can do is now we can really easily check the rank of lambda by just sort of summing up the elements of the main diagonal of lambda. Right? The main diagonal of lambda just contains zeros and ones, so we sum up the elements of the main diagonal. As a matter of fact, there is a function, a matrix function, which does exactly that, and it's a so-called trace function. The trace function sums the elements on the main diagonal of a matrix, any matrix. Okay, so trace takes the sum of the elements on the main diagonal of a matrix. Here it's a diagonal matrix, though there are only non-zero elements on the main diagonal, but the trace operator works nevertheless. Okay, so we learned that about idempotent matrices. They have eigenvalues either 0 or 1. Now, equipped with this knowledge, we can actually now turn to showing the result that we want to show. This result 2a. Page 89. Okay, and the statement was, okay, x is used. X is this vector of standard normally distributed random variables which are independent, so they have a zero covariance, and we take this quadratic form which invokes a matrix A, and we need this matrix A to be, first of all, we want to have a matrix that is symmetric and square, and the point is this matrix should also be an idempotent matrix. So the statement is that this quadratic form comes out as a chi-square distributed random variable if you use a symmetric square and idempotent matrix. Now suppose for the time being that A is just symmetric and square in this quadratic form, so we can write this quadratic form using the spectral decomposition that we've encountered earlier. So for that purpose, we use result R1b, spectral decomposition. Okay. Now let's define some auxiliary variables. Let me call them y. Okay, y is an n by 1 vector, and this vector is resulting from taking x and multiplying it with c prime, the matrix that contains in its rows the eigenvectors of the matrix A. Okay. And similarly, y prime is given as a transpose of y, and using standard rules of matrix multiplication, I have y prime coming out as x prime c. Okay. Now, what we also get is some idea about what the random variable y actually is, and particularly what the expected value is. So it would be c prime, the expected value of x, but x is standard normally distributed. So we have c prime 0, so the expected value of y would be 0. And what about the variance covariance matrix of y? Well, it would be c prime, the identity matrix, which is the variance covariance matrix of x, c, and that would be the identity matrix as from an earlier result, or R1a actually, the orthogonality of the eigenvectors of a symmetric and square matrix, right? Which is used here. So we can conclude, as a matter of fact, that we deal with standard normally distributed random variables, which are also independent. So like x, y is standard normally distributed, is a vector of standard normally distributed random variables, which are uncorrelated. So y shares this property with x. Why have we done that? Well, we've done that because we can write this, the expression that we have started with, using the y's instead of the x's and the c's. Okay, so I'm using y prime here, I have lambda here, and I have y. So that would be a vector, y1, yn, a vector of these normal variates. And recall lambda, always important to recall what lambda is. Lambda is this matrix which collects on its diagonal the eigenvalues of the matrix A. Okay. Now take a look at this object. What this means. A y as just a vector. We multiply it with the lambdas, so we can write this expression, this quadratic form, in a straightforward fashion, because the matrix in the middle is a diagonal matrix using a summation. So we sum from I equal to 1 till n. We get yi squared, and we multiply with lambda I. Okay, that's the way to write this expression using a sum. Now, yi are standard normally distributed random variables. We square them. So yes, in principle, what we get here from this quadratic form is we are going to sum up the square of standard normally distributed random variables, but only if the lambdas are 1, which would mean that I sum a square of a standard normally distributed random variable, or 0, which means that this variable is out of the summation in the first place. Okay, so the expression is going to be chi-square distributed only if the lambdas are either 0 or 1. Right? If they are either 0 or 1, then this expression y prime lambda y, or x prime c lambda c prime x, which is what we started with, actually is a chi-square distributed random variable. Okay, and this is essentially what we want to show. So x prime a x comes out as a chi-square distributed random variable only if the matrix A actually is a symmetric, square, and idempotent matrix. Now, what about the degrees of freedom of that chi-square distributed random variable? Well, it depends. It depends on how many non-zero, how many eigenvalues which are actually 1 are in lambda. So these guys can be either 0 or 1, and if some of them are 0, then I'm actually summing up not n standard normally distributed random variables, but less of them, but less than n. Okay, and it's actually the number of eigenvalues which are 1 which determines the rank of lambda, but the rank of lambda determines the rank of A, right? So the chi-square distributed random variable has degrees of freedom which is equal to the rank of A. Okay, but the rank of A is the same as the rank of lambda, and that's the same thing as the trace of lambda. In other words, it's equal to the number of non-zero that is equal to 1 eigenvalues of this matrix A, this symmetric and square and idempotent matrix that we use to construct this quadratic form in the first place. Okay. And as a matter of fact, this is stated or was stated in result R1D, where we took a look at the rank of the symmetric and square matrix and found that it's actually determined by the number of non-zero eigenvalues of the matrix sigma, symmetric and square matrix sigma. Now here we have the specificity that these eigenvalues can only be 0 or 1 because the matrix that we're dealing with here is an idempotent matrix, and all this together shows in a way the result 2a on page 89 in the script. Okay, so that's the derivation, the second derivation surrounding the J statistic, and there's going to be a third one which continues with this discussion. Okay, thank you very much and enjoy watching the video.